Lastly, let's summarize the results of the weak acid strong base titration. Over the past series of lectures, we calculated the pH at 4 different points in the titration of acetic acid with sodium hydroxide. And what we found was before adding any sodium hydroxide, we had a pH of 2.38. After adding 10 milliliters of sodium hydroxide, the pH went up to 4.15. After adding 25 milliliters of sodium hydroxide, the pH went up to 4.75. And at the equivalence point, when we added 50 milliliters of sodium hydroxide, the pH was 9.23. So one of the things that's worth looking at as we compare the results from these 4 different points is as we go from point 1 to point 2, we see a very large change in the pH from adding just 10 milliliters of sodium hydroxide. However, when you go from point 2 to point 3, you added another 15 milliliters of sodium hydroxide, but the change in pH was much smaller. Why would that be the case? When you're in this region where you're at around the points, between points 2 and 3, you have a buffer. I'll recommend that you take a look back at the videos where we calculated the pHs at these 2 points. And when you look back on these videos and when you look back at your notes, what you'll see is that at these 2 points, the sodium hydroxide reacted with the acetic acid to produce acetate ion. And after all of the sodium hydroxide was used up, you had both acetic acid and acetate ion as major species. So within this portion of the titration, you have a buffer. We refer to this as the buffer region of the titration, where both the weak acid and its conjugate base are major species. And so because you have a buffer that's generated at this point in the titration, you'll have a fairly small change in the pH as you're adding more and more of the sodium hydroxide. However, things don't remain a buffer forever. As you continue adding more and more sodium hydroxide, you get to a point where you consume all of the acetic acid, and then it's no longer a buffer anymore. It does not resist pH changes. So that's why we see a big jump up in the pH when we reach the equivalence point. Once you've used up all of the acetic acid, it's no longer a buffer, and so the pH spikes. We also noticed in the calculation for the pH at the equivalence point that it was greater than 7. So even though you've neutralized all of the acetic acid, that does not mean that your solution is pH neutral. When you do the titration of a weak acid with a strong base, I'll remind you that at the equivalence point, all of the HA consumes all of the OH minus, and your major species in solution at the equivalence point are your metal cation, which is just a spectator, and the conjugate base of the weak acid, right? The conjugate base of the weak acid is a weak base, and so at the equivalence point, what you have is a weak base in water. This is why the pH at the equivalence point for a weak acid strong base titration will be greater than 7. Now, you could calculate the pH at every single volume of NaOH that you would add, going from 0 beyond 50, and you would get a titration curve that looks something like this. And we can notice a few trends in this titration curve. One thing that you notice is, right, we start off with our pH, somewhere around 3 before you begin adding sodium hydroxide. And as you add NaOH, the pH kind of rises pretty quickly because initially you do not have a buffer. So big rise in the pH, but as you add sodium hydroxide and it reacts with the acetic acid, you form the acetate ion. When you have both the acetate ion and acetic acid as major species, you reach this buffer region of the titration curve where the pH is fairly stable upon the addition of further sodium hydroxide. So in addition to that, because you have a buffer, the pH is controlled by or can be predicted or calculated by the Henderson-Hasselbalch equation, which says that pH is equal to pKa plus the log of the ratio of A minus over HA. Now, that log of A minus over HA is a relatively small number, right? Because when you take logarithms, that really serves to kind of bring the number down. And so what you end up with is a situation where the pH is roughly equal to the pKa. It's very similar to the pKa in this region. So in the case of acetic acid, that's going to be somewhere around 4.75 through this region. And at the half equivalence point, it will be exactly equal to 4.75. Then, as you continue adding sodium hydroxide and you get to the equivalence point, you're going to see a steep rise in the pH because it's not a buffer anymore. All of the weak acid has been consumed, and so a steep rise in the pH, and the pH at the equivalence point is greater than 7. So in this graph with the numbers shown here, right, it's not exactly the same as what we had calculated, but again, it's greater than 7. It's somewhere around 9, which is about where we calculated it to be. You can take a look at the titration curves for several different acids with sodium hydroxide, and that's what this graph shows. Several different weak acids. Each one of these lines represents a different weak acid being titrated with sodium hydroxide. And they have different Ka values, and so as a result, the titration curves are going to look quite different. But some things that are the same, that are worth noticing in this is when you look at the half equivalence point, which if the full equivalence point is at 50 milliliters, the half equivalence point is at 25 milliliters, the pH will be equal to the pKa. We know that from the Henderson-Hasselbalch equation. Because different weak acids have different pKa's, you're going to have different pHs at the half equivalence point. And we could draw in the line showing where the half equivalence point is. And if you were to have a weak acid that has a Ka of 10 to the minus 2, then pKa is 2. And so at the half equivalence point, the pH is 2. If instead you had a weak acid with a Ka of 10 to the minus 10, then pKa is 10. And at the half equivalence point, the pH will be equal to 10. So this is one way that you can distinguish between various weak acids, and one way that you could determine what the Ka or what the pKa of a weak acid is by looking at what the pH is at the half equivalence point in a titration. Lastly, just as a recap of the strategy for solving acid-base chemistry problems that we've been discussing throughout Chapter 7 and throughout Chapter 8 so far. You want to always begin by writing the list of major species that you have in solution. That allows you to figure out what type of a problem you're dealing with, and it allows you to devise the strategy that you're going to use to solve the rest of the problem. Then you're going to look to see if you have H plus or OH minus, because if either of those are present, they take top priority, and they are going to react immediately and to completion. That means that you have a stoichiometry problem, right? That's what the to completion part means. And when you have a stoichiometry problem, you'll need to set up a before and after table and make sure that you're using moles when doing the stoichiometry. If you don't have H plus or hydroxide, then you don't have to worry about doing a stoichiometry problem. You could just skip to step 4 in this strategy. All right, so let's say that you had H plus or hydroxide, you reacted immediately into completion using before and after table. Then what you're going to do is rewrite the list of major species that are remaining. Because every time you make a before and after table, whatever your limiting reactant is goes to 0, so that has to be removed from the list of major species. It's also possible that you generate a new species when you do this chemical reaction, and so you have to take that into account as well. So rewrite the list of major species to see where you go next after the H plus or hydroxide reacts. And then you're going to ask yourself if you have a buffer. If you do, then you can use the Henderson-Hasselbalch equation to find the pH. If you don't, and you do not have H plus or hydroxide as major species, then there's an equilibrium reaction occurring. Write the reaction between the strongest acid and the strongest base. This is an equilibrium reaction, and so you're going to set up an ice table to solve the problem. You'll have to figure out if you have a Ka or a Kb that you're dealing with, and what the value of Ka or Kb is. And when you make the ice table, you must use concentration and molarities, right? Do not use moles in the ice table. If you don't have a buffer and you see H plus or hydroxide as a major species, then you're not dealing with an equilibrium reaction. You don't even really need to write a reaction of any kind. If you have H plus or hydroxide as a major species, then you can simply find the pH by determining the concentration of H plus or hydroxide, right? And then take the negative log to get either pH or pOH, and then you'll get through to the solution to the problem. So that wraps up acid-base chemistry. Next, we're going to go on to talk about solubility product.